Okay, so Bobby Kennedy was shot in 1968. The movie was released in 1997, so I guess that means that Jupiter is 30 light years away. A little inaccurate. But I get it. If it was accurate, we would have been out of the solar system in about 5 seconds and just been listening to radio waves on a field of stars, which is visually boring. So yeah, I get it. It's still a brilliant bit of filmmaking, and it really makes you think about, how far out into space our radio waves have traveled. How many stars have our radio waves passed, and how many planets might be orbiting around those stars. And on any of those planets, is anyone listening? One location that was featured prominently in the movie Contact was the Arecibo Radio Observatory, which unfortunately we did lose last year when the instrument panel fell down into the dish down below. But maybe it'll come back someday? Fingers crossed. But from its construction in 1969, it did do some great science. It was the first scientific instrument to detect a binary pulsar. It made a map of Venus that showed signs of volcanic resurfacing, and it kept track of several near-Earth asteroids. But what it's probably best known for is SETI, the search for extraterrestrial intelligence, probably partly because it was featured in that capacity in the movie Contact. In real life, Arecibo, of course, received many signals from deep space. None of them were of an intelligent origin that we're aware of. But in 1974, Arecibo attempted to send a message the other way. They modulated the frequency of a radio transmission to encode pictures of DNA, a stick-figure human, and Arecibo itself, among some other stuff that I mentioned in a video from years back. It was created by Carl Sagan and Frank Drake, and it was mostly symbolic. They aimed it at a star about 21,000 light years away, and in fact, the star will have moved by the time the signal reaches there. That was intentional. But as the opening scene of Contact points out, we've been unintentionally putting radio waves into outer space for nearly 100 years. The first commercial radio station went up in 1920, and we've just kind of been shouting into the void ever since. That means there's a radio bubble that we've created, a sphere of influence, if you will, 200 light years wide. That's friggin' huge. Just think about all the stars that might be inside that bubble, and all the planets in those stars. What would that look like? Turns out it would look like this. Or, well, hang on, let's move in a little closer. There it is. That's 200 light years across. Go us. I don't know, it makes me think of that scene in Titanic when they shoot off the signal flares trying to get help, and then they kind of scale it back, and you can see that there's just a tiny little flare in the middle of the vast expanse of the Atlantic, just kind of just nothing. It's a weird connection, but my brain did it. So sure, next to the entire galaxy, that's next to nothing. But it's not just about distance, it's about stellar density. There's still plenty of room for stars in a 200 light year bubble. There's only one star system within 5 light years of Earth, and that's Alpha Centauri, with 3 stars and at least 2 planets that we know of. Expand that out between 5 and 10 light years, and 8 more systems appear. 2 of these systems are brown dwarf stars, and one's a white dwarf. Counting the sun, this gives a total of 15 stars in our 10 light year neighborhood. 4 can be seen with the naked eye. To see the others, you need a telescope or a good pair of binoculars. Now, it's worth noting that 3 of the stars on that list are those brown dwarf stars that I was talking about, and we didn't even know they were there until between 2011 and 2013. So even nearby stars can be hard to spot. And distant stars can be even harder, so we have to kind of do an estimate to get a full figure of our radio bubble. An estimate by astrophysicist David Palmer in 1998 concluded that the bubble contains some 14,600 stars. He based it off the stellar density within 5 parsecs of Earth, or 16.3 light years. Now, he picked 5 parsecs because the most accurate star catalog that we had at the time only went out that far, but of course, a lot has changed since 1998. The most up-to-date star catalog we have right now is the Gaia catalog of nearby stars, and it's accurate up to about 10 parsecs, which is 32.6 light years. And this catalog suggests there are 464 stars within a 10 parsec bubble around Earth. Doing some math, that gives a stellar density of 0.11 star per cubic parsec, only 1/100th less than Palmer came up with. So that brings us to an estimate of 13,332 stars within a 100 light year radius of Earth. Now, that's nothing to sneeze at. For perspective, pretty much the most number of stars that you can see with the naked eye is about 4,500 stars. So take the most number of stars you could possibly see in the best conditions with the naked eye, double it, and then add 4,000 stars. All inside that tiny little dot. Pretty crazy. So is 13 to 15,000 stars the answer to our question? It's part of it. I mean, that's how many stars our radio transmissions have reached. Now, whether or not there's anybody at those stars listening to us, that's a whole other set of questions. 50 to 75% of stars in the Milky Way are thought to be red dwarfs. These are dim K or M class stars at the bottom right of the Hertzsprung-Russell diagram that group stars by brightness and heat. To give you some M class stars, the 5% of stars in the Milky Way to us, that's a whole other set of questions. 50 to 75% of stars in the Milky Way are thought to be red dwarfs. These are dim K or M class stars at the bottom right of the Hertzsprung-Russell diagram that group stars by brightness and heat. To give you some idea of the scale, our sun is a G class star with 2 to 3 times the heat and 3 to 30 times the brightness of a red dwarf. So in our 13 to 15,000 stars in our bubble, we can expect anywhere from 6 to 11,000 of them to be red dwarfs. The problem with that is that most of the rocky planets around red dwarf stars have to orbit so close that they become tidally locked, which I actually talked about in my eyeball planets video. Eyeball planets aren't the best candidate for life because that basically means that one side is frozen and the other side is scorched, and there's just sort of a ring around a polar orbit of the planet where liquid water could exist. Which doesn't totally rule it out. There's still a possibility that life could spring up and evolve there, but another problem with red dwarfs is that they're highly volatile. Red dwarfs have a tendency to throw off huge solar flares that could possibly strip off the atmosphere of a nearby planet. Now, this doesn't mean that life couldn't have possibly sprung up on any of those planets. I mean, hell, we might even be able to survive on one of those planets. But the possibility of it being stable enough for life to evolve to the point of building radios, it's not the best bet. So right off the bat, we have to rule out the vast majority of the stars in our bubble. Now, there are some sun-like stars out there. There's some pretty good candidates. But before I get to that, there is one other major problem we have to contend with. This is known as attenuation, which is basically the weakening of light and electromagnetic signals as they travel through space. Now, you've probably heard me refer to the inverse square law on this channel or in other places before. It basically says that the strength of the light is inversely proportional to the square of the distance from the source. Put into something resembling plain English, the further a light travels from a point source, the more it dissipates and the weaker that signal becomes. Take Voyager 1. It's now 14 billion miles away, which is about 2/1000th of a light year. It's sending a signal back to Earth at a power of 22.4 watts, and by the time it reaches NASA, the signal has a strength of 1/10 of a billionth of a watt. Like, it's crazy that they can even detect that. And that's only 0.002 light years away. At 100 light years away, our signals might be completely indistinguishable from the cosmic microwave background radiation. In order for an alien civilization that far away to even detect us, it might require a planet-sized dish. Now, of course, when you're talking about aliens, there's always that magic alien technology that's so far advanced from what we can do that it makes it possible for them to do that. Fair enough. But even if the attenuation problem didn't exist, there's still the habitability problem. So going back to where I was going before, how many rocky planets around sun-like stars are there in our 100-mile radius around Earth? In another paper from last year, in 2020, some scientists from SETI and NASA calculated the number of rocky planets from around sun-like stars are there. So going back to where I was going before, how many rocky planets around sun-like stars are there in our 100-mile radius around Earth? In another paper from last year, in 2020, some scientists from SETI and NASA calculated the number of rocky planets in the habitable zone of stars that are G and K class stars within 32.6 light years away, in other words, 10 parsecs. And their answer, drum roll please, Four. Now, if you apply that same density out to about 100 light years away, then it comes out to about 115 stars. But once you go through the Drake equation and rule out this and rule out that, and then you factor in the fact that, you know, these stars have been around for billions of years, and what are the possibilities that an advanced civilization would evolve in the same 100-year window that we did, it's not the best of odds. Now, that doesn't mean that nobody out there knows that we're here. You know, we've discovered plenty of exoplanets, and none of that had anything to do with any intelligence signals that might have been coming from those planets. We did it, mostly, using the transit method. Very briefly, the transit method is when you watch a star and notice it dimming on a regular basis. That usually means that there's a planet passing in front of it. Currently, what we learn from the transit method is pretty limited. We get its size, how far away it is from the star and all that. But when the James Webb Space Telescope goes up, we're going to be able to see a lot more than that. We should be able to determine what's in these planets' atmospheres. When a star's light passes through a planet's atmosphere, the various elements in the air absorb the light in different ways. By splitting that light with a prism, we can pinpoint what wavelengths have been blocked and know what elements are present. And of course, if we find things like oxygen, carbon dioxide, and methane, then we'll have a pretty strong suspicion that that planet could support life. And similarly, we presume an alien civilization would be able to see us passing in front of the sun and see that there's something interesting happening here. meaning there's a band traveling out from our star in 360 degrees where any stars in that band would be able to see the Earth transit and maybe determine that there's life here. And that even has a name. It's the Earth Transit Zone, or ETZ. So a recent article in the journal Nature put together a figure for the number of stars that are actually inside of our radio bubble and inside the ETZ. The author searched the Gaia catalog for targets in the Earth Transit Zone and found 1,402 stars in the zone now, and 1,715 have been there in the last 5,000 years. All of these are within 100 parsecs, or 32.6 light years of Earth. And when they restricted the radius to 100 light years, they found 75 stars that fit their category. Now, all of these were within, again, 100 parsecs, or 32.6 light years of Earth, but then once they ran it through all their filters and picked out sun-like stars and, tried to figure for the ones that could both hear our radio signals and were in the ETZ, it came out to 46 stars. Now, at the time of this recording, none of those 46 stars are known to have a planet. But SETI telescopes are starting to focus more on those stars, so we may see something soon. And the first exoplanet host that we know will enter the bubble soon is Teegarden Star. So Teegarden Star is 12.5 light years from Earth, so it's well inside the radio bubble, but it is not inside the ETZ. It'll enter the ETZ in 2050, so maybe by the time that happens, they'll be able to pick up our signals from the 2038 Winter Olympics. Now, Teegarden Star is, yet again, a red dwarf, but Teegarden B and C are both in the habitable zone of that star and are thought to have thick atmospheres. Now, there are 3 stars that are currently within the Earth Transit Zone, but they're not quite inside of our radio bubble. They should start hearing our signals around 2159. But if any of those stars have an inhabited planet and a radio dish several times the size of its star, it might be able to pick up the Giants beating the Yankees 5-3 in the 1921 World Series. Let's hope they're fans of High Pockets Kelly. Now, the irony of this whole discussion around radio signals is that we're actually getting a lot quieter in that respect. Most of our communication is done digitally these days over wires. We don't really blast out giant broadcast signals to cross continents like we used to. Double ironically, we communicate mostly through satellites these days, which means we're actually pumping our signals up into the air, but they're only having to go up, 100 or so kilometers or a little bit more than that. They're not meant to cross thousands of miles of land. So much communication is done these days over wires and short-range communication that we're actually kind of going quiet after about 100 years of screaming our lungs out. This literal radio silence is one of the explanations that some people have for the Fermi paradox. Like, maybe the reason we're not seeing a lot of radio signals bouncing around from other civilizations is because they all moved beyond radio. Maybe radio communication is just a short moment in a species' evolution. After a blip of making a lot of radio noise, they just go quiet. Maybe the solution to the Fermi paradox is that the universe got cable. So with respect to Carl Sagan and Robert Zemeckis, the central conceit in Contact, the idea that our radio signals will be picked up by an alien species and bounced back to us, is optimistic at best. But it does make you think about how little we've actually reached into the universe, and how far we have to go. Of course, you don't have to go far into the universe to learn more about it. You can do that from the comfort of your chair if you check out the astrophysics course on Brilliant. All right, so I've been talking about Brilliant for a really long time now, and maybe you checked them out once upon a time and were thinking, maybe if it was more interactive. Well, guess what? It's a lot more interactive now. They've actually added a lot more functionality and interactivity to their quizzes, which only helps boost the understanding of the concepts involved, especially in some of the fundamental courses, which sort of set the foundations for everything to come. And in case you're wondering, I do actually refer to Brilliant to help me to understand some of the stuff that I do in these videos. Like, for example, today I looked at the astrophysics course because there's actually a segment in there all about radio and electromagnetism and how it travels through space. And they make it easy to make learning a habit, so you can do it on your mobile device or even offline, so whenever you're waiting for food or something, you can bang out a problem or two. Now, if you want to get a taste of what I'm talking about, they have free daily brain teasers, and you can do the first section of any course for free, so you can see what they're all about. But if you do sign up for the premium subscription that gives you access to all their courses, and you're one of the first 200 to do so, you can get 20% off if you go to brilliant.org/answerswithjoe. It's just a really cool way to learn things, and like I said, they've added a whole lot of stuff, so if you haven't checked it out lately, I definitely suggest you go check it out. It's brilliant.org/answerswithjoe. Links down in the description. All right, big thanks to Brilliant for supporting this video, and a huge shout out to the Answer Files on Patreon and the channel members on YouTube that are supporting and helping to grow things and being really just forming an awesome community. They're cool people. I got some names I need to murder real quick. So these are some members that signed up recently. We got Pieter Bon, Julian Robert Lacado, I'm nailing it already, Elizabeth Wagner, Alexithia Waterworld, Vivek Ramesh, Jessica, Joseph Stokes, Tobias Tomila, Daniel Ermagren, Kevin G. Barks, Sawyer Mirage, Rosalie Abel, Christina Rose Nemo, Seth Developments, Aaron Jones, Sean Patrick Thompson, Dharma Hetherington, and Lilith Esme. Thank you guys so much. If you would like to join them and get early access to videos, get little cool avatars by your name and stuff so you stand out from other people, just click the little join button down below. Please do like and share this video if you liked it. If this is your first time here, Google thinks this one's right up your alley, so check that out. We got several other on the side with my face on the thumbnails, and if you enjoy them, if you want to see more, I subscribe. I do come back with videos every Monday. I think that's it for now. Thanks you guys for watching. Go out there and have an eye-opening rest of the week, and I'll see you next Monday. Love you guys. Take care.
Okay. Okay, bye. Bye. The number one. Наоборот, да нет. Да нет. Ну наоборот, значит. Это даже не пародия, наверное, просто. Я могу просто это смотреть. Продуктовый, говорит, за собственно, что это такое вообще? Ну нет, как бы, как так это? Ну таланты просто здесь, что ты? Все нормально. Друзья, говорит, просто, да, понимаю. Нет, нет, не сделать, нет, просто деньги зарабатывают люди, понимаешь? Это должно быть привлекательно как-то, да. Талантливо или что там. Да это не важно. Ну это, ладно, ладно. Да. Не, ну разные люди есть просто. В целом характеристика. Да, понятно. Тренд такой, да, трендец. Нет, деньги надо, понимаешь? Это как бы никто, всем вообще похер, что там, смеешься, да. Понял, ну, наверное, да. И что это? Да, он такая. Так это есть оно, да? Ты что, охерел, что ли? Да нет, да больно надо, что ты. Ну это шокирующе как бы. Понимаешь, если ты если для тебя это нормой будет, если ты, да, понимаешь. ну как бы, ну смотри сам, что только не было, он, да, правильно, да. А это для нас шокируйся, а так это нормально. Понятно, да. Ну, это размытие. Рублей, да. Нет, нет, ну не порвало, это есть на самом деле. Ну нет, ты сам так делаешь, да. Это есть на самом деле, понимаешь, что ли ты понимаешь, что ли ты? А, я это что-то не делал еще, да? Что сам... А, кстати говоря, да. Потом не восстановишь уже, это сложно. Ну, подожди, я опять... Не совсем, да. Интересно. Что-то у меня мозг где-то кочкой уже. Да, наоборот, да. Время опять летит, блин, тратится все, блин, ну... рапорт. Рапорт. Thank you.